Uh, all right. This is the. Uh, I am Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and today we are here to discuss some problem based on the week three lectures, which are covered under the course Essentials of Oxidation and Reduction Reaction, as well as carbon-carbon bond formation reaction, and its application in organic synthesis. So we are learning this course on the NPTEL as well as SWAYAM platform, and we'll just discuss here some problems based on the topics which are covered in the week three. So these are the I will show here some slides which are already covered. So just to revise, and so you can able to solve the assignment questions. So this is the first slide, and in which the I have purposefully kept here to show what is the how this reaction of the IBX. IBX is the uh, hypervalent iodine reagent which is used for the oxidation, right? And we know the reaction of this IBX with the alcohol. So in let's say we have used the one equivalent of the IBX, it gives the formation of initially the keto, right? And again the another equivalent will which helps to form the alpha beta unsaturated keto derivative, right? So this is the reaction, and in terms of this IBX at 60 degrees Celsius in the DMS or the toluene solvent, so it gives the product in this manner. And in the similar manner, in this case also, if you use the 4 equivalent, so what will happen? It gives 2 alpha beta unsaturated bond across this. Let's take the example of cyclohexanol, and this alcohol on addition of the 4 equivalent of the IBX, right? So it gives the uh, it gives the two equivalent of sorry two uh, double bond, which is alpha beta, right, located at the alpha beta position in this cyclic ring. And if here another similar example, that like only on the instead of cyclic ring, here give the on the heptane heptanol, right? So here in place of two equivalent, it gives the double alpha beta unsaturated keto, right? So, and in place of two equivalent, it gives only on one side, alpha beta unsaturation on only one side. So, help you can take lead from this and able to solve the assignment question. The next slide I have purposefully kept based on the Prevost reaction, uh, and the another will be on the Prevost, as well as the one slide is for Woodward, right? So, the Prevost reaction is the, if you look at the reagent used in the Prevost reaction, is this Prevost reaction is used for the oxidation of alkene to the 1,2-diol, right? So this is the alkene, and this alkene, this is the starting material 1, and in presence of the pH silver salt of C double bond O Ag. So this is the, I just enlarge the structure. Silver salt in presence of iodine, and the solvent here is the benzene. Although benzene nowadays it is banned in India to use as a solvent, so there are many other options like toluene and other solvent we generally use in this case. So if you look at the reaction, so this alpha beta, sorry, this double bond converted into the diol, uh, and in the first step we add this one, and the second step there is a KOH water, so it gives the formation of 1,2-diol, and this 1,2-diol is particularly anti to this double bond is a anti, that is, which is, if you look at the hydroxy group and this hydroxy group, they are exactly opposite to in terms of stereochemistry. So we get here the anti product as a major product. And if you go to the mechanism step by step for this one, so this is the catalytic amount of iodine. So when you add the catalytic amount of iodine and the silver salt, so this catalytic iodine and silver salt form a complex in which the one iodine is delta positive and one iodine forms a delta negative charge, right? And Ag is here, it is already it's positive and negative salt of this benzoate. So it forms a complex in this manner. And since this iodine is electrophilic, so I'll just change the color. So if you look at this iodine, this is slightly electrophilic. So what happens? This double bond react with the iodine. It forms a complex, iodinium complex, and this complex is then uh, the form complex get attacked by the benzoate, and this benzoate do the addition. So I will just put on again the presentation mode. So this benzoate attack to in the antiphation to the iodinium cation. So the addition of this benzoate gives the form in the antiphation gives the iodinium this group and as well as the benzoate group anti to each other, right? So this is anti addition, and when this anti addition takes place, we have the it forms the though already this carbonyl group it has slight polarization in like the C positive and the oxygen negative. So the O negative attacks on the center in which the iodine is attached, because iodine is already good leaving group, right? And again we have added the silver salt. So the silver salt plus iodine, this complex is very labile. So the addition of this um, carbonyl takes place to the across this carbon center, and it form an intermediate. So this first intermediate, which is formed by adding, which is a syn fashion. So if you look at the stereochemistry of this both oxygen, because it attack on the same side, right? So it will be a syn, obviously. And in next step is the addition of the KOH and water. So, uh, but before going to the reaction with this KOH water, this is the second step. So again, we have the this abundant benzoate, silver salt of this benzoate, right? So this benzoate attack in the antiphation to the previously uh, substitute carbon. This can attack either the carbon 1 or carbon 2. It doesn't matter in terms of stereochemistry. So let's say it attacks on the carbon 1. So it gives the formation of this benzoate, which is the first benzoate and the second benzoate. These both there in the antiphation, and the hydrolysis of this benzoate takes place when we do the workup with the KOH. And when they stir the reaction mixture with the KOH, it gives it hydrolyze this ester. So this is a simple ester hydrolysis reaction. The hydroxy group attacks the hydroxy attacks on the carbon, give rise to the negatively charged OH, O minus, and which abstract the proton from the solvent. This is obviously here in this case is the water. And when it abstract the proton, it forms the alcohol. And this alcohol form in this reaction is a trans alcohol. So this is the example. It gives stereoselectively trans alcohol or trans 1,2-diol as a product. So this is the Proust reaction. And if you look at the another reaction is the Woodward, and the Woodward reaction is also the similar. Only in this case, the instead of here we add the water in the reaction. Initially, in the first reaction, we see there was no any water. Here, water and water and acetic acid is the co-reagent. Previous in the Proust reaction, there is. So if you look at the reagent, there is silver salt of benzoate and catalytic iodine and the benzene. This was the reagent. But if you look at the Woodward modification of this reaction, in this one, we add the silver salt, catalytic iodine also there, but the solvent here is the water. Initially, it was benzene. So what happens in this one? So we get the such intermediate, and later we get the cis diol 1,2-diol as a product, right? Cis 1,2-diol as a major product. So if you look at the mechanism of this reaction, it is the first step is very similar, right? We got the intermediate that we have already seen. yeah, in case of the pre-host diol formation. So this intermediate one get attacked by the water because in reaction there is present water is present. So this water is if you look at the size of this water, so it can easily go inside this intermediate and attack on the electrophilic position, and and also there is O negatively charge. So negatively charged also. So when it attack to this position, this is a kind of a good. So ignore this one as of now. So if you so this is not required at this position at this point. So if you look at this water, this what the size of water is less bulky, so it attack here. So this attack is not that much easy because water is present in this reaction. So once this intermediate drop, it is very readily get react with the water and form a such intermediate in which the it forms a double bond back and give the this OH in the same side to this benzoid group. So if you look at here, you can see there is migration of this benzoid group, right? So this kind either OH can be this, or if you look at another possibility, so this can be OH also. But if you look at the stereochemistry seen or trans, it will be remain same. So this one, so this both OH is on the same side. And if you look at the next step is the hydrolysis with the KOH water. And once we do the hydrolysis of this reaction, uh, of this intermediate, it will give convert into the diol. So the next step is also the same. This OH negative, this OH minus attack on the electrolytic center of this ester and gives the diol. We get the diol. In this case, we get the cis diol. So this is the Woodward modification, and hope there is one question in assignment based on this one, so you can able to solve that question. So keep in mind. So I will just summarize this slide. So I will just insert one slide in between. So in the pre-host and Woodward, I will just make it in the form of table. So in the pre-host, and you can make it complete. So what you have is the silver salt of C double bond O Ag. The catalytic iodine was also there, and the solvent was benzene or toluene, right? And in the next step, this is the first, and in the next step, KOH, right? KOH water. So this is the next step. We add in the next step. But in the Woodward, so what we add? We add the silver salt of benzoate, and we add here, in this case, the silver salt plus catalytic amount of iodine. And in the same, the reaction was in the catalytic, sorry, the water as well as acetic acid, right? And in the second step, we add the KOH water. That is hydrolysis step, right? So this pre-host modification, pre-host 1,2-diol formation gives anti-diol, and this gives syn diol, right? So you can keep this remember. So this is the Woodward and pre-host modification. So this is also the important in terms of for your CSIR as well as the for your assignment, solving the assignment. And next, the next topic is the same that we have already on the first slide that we have discussed regarding this Dubin-Mincho rearrangement with the IVX. So what happens in this reaction? So I will take this example, uh, the same example. So here, when the alkyl lithium react with this alpha unsaturated ketone. So this is alkyl lithium is, let's say, methyl or ethyl lithium or butyl lithium. So this is hard base, right? So it is CH2 minus. So it is definitely hard. So there will be reaction of the hard as well as soft as we already know, right? So which is hard center here, this is carbonyl center, so it attack directly on this one, so we get the alcohol in this manner, so which is directly the 1,2 addition, right? So in this case, let's say if you add the copper salt at that time, so this center will be behave as a this nucleophile will be then will convert it into the copper salt of Cu plus, and this CH2R minus, it converted into soft center, and this soft center attacks on the 1,4 position. So that is fourth position. So at that time, the addition takes place at this position. But right now, we are using the R lithium, which is hard base. So it takes place on the second position, that is on the carbonyl carbon. And it convert into the tertiary alcohol. And when we use the IBX, so that we already know the structure of IBX, right? This is the IBX structure of IBX. And this alcohol, the OH, as mentioned, is react with the iodine. It forms, it releases the OH minus. So this OH negative will get released, not in the form of OH minus, it go remove in the form of water, H2O. Right? And then it convert into the intermediate in this fashion, followed by the, so we have here the double bond, right? So what happens? So the O negative uh, is also present, this one, right? So the one of the O negative abstract the proton, the sorry, O negative is attack on the, so in the iodine there is O negative. So this O negative attacks here, gives a kind of rearrangement reaction, and this the bond between carbon and oxygen get cleaves and form it again I double bond O. So in this case, what happens? The intermediate that I will draw here. Take the other thing. So this will be the oxygen. Here is hydrogen, and this bond shift here. The R remains here, right? This reagent form, and here there is iodine O negative, and the remaining part of this reagent will be in this fashion. So I will not draw fully, and you can see the other part, right? So what happens? The next step is this O negative abstract again this proton. So this proton abstraction takes place, followed by the electron donation to the formation of the carbon oxygen double bond, and this bond get eliminated, and electron pairs goes to the iodine. It gives the oxidized product. So here this proton is abstracted. So we get the we see the carbon carbon was initially on this position. It get migrated to this position by using the two steps. This is the first step was the addition of this alkyl lithium, and in the second step it is the IBX. So this within these two steps, it forms the carbonyl carbon group get migrates from 1 to 3rd position. So this is the Daubin-Mincho rearrangement reaction. This happen with the IBX. And also there are some, if you use, if you remember there with the PDC, also this such reaction can occur. I will show that also example in the latter part of this presentation. So hope this also help for you to solving the question, one of the question from the assignment. All right, here I have summarized what we have already seen. This is the obviously the Prevost uh, reaction. It gives the formation of this is the detailed mechanism that it gives the formation of anti-alcohol, and there is yeah, this here it is. This was the intermediate. Upon hydrolysis, it obviously gives the OH. OH. The Woodward gives the syn alcohol, and Prevost gives the anti. Right. So this is the uh, steps involved in this 1,2-diol formation that we have already previously studied. So in this by using this method, this Woodward as well as the Priost reactions, we can able to see the one two. We can able to make the one two diol, right? So if you want to make the uh, one at one position diol and another position amino group, so there is amino hydroxylation. This is one of the reaction. So you can also look for this reaction. So you can remember this reagent. So let's say we have this kind of double bond alkene. This the alkene 1 mole% that is catalytic osmium tetroxide and a salt which is tosyl chloride salt, right? This salt as well as the reagent BnNMe3. This is also one of the salt at 60 degrees Celsius in chloroform solvent. It gives the amino hydroxylation. So in previous reaction, as you see, we get the dihydroxylation like syn as well as the anti. And in this reaction, we get the amino hydroxylation, and this amino hydroxylation occurs in the syn fashion. So if you look at the stereochemistry, both are the beta. So we get this stereochemistry by using this reagent combination. And this is the active reagent in this one. So osmium tetroxide as well as this reagent. It forms the in situ this kind of reagent, and TS stands for entire tosyl group. So this is also another modification of conversion from alkene to uh, difunctionalized group. That is, we seen 1,2-diol as well as here 1,2-amino hydroxyl group. Then we move directly to the oxidizing agent. So I have summarized, I have added some uh, reaction of oxidized reagent here. So I will show that reaction first, and then we move to the problems in the assignment. So this is first reaction is ozone lysis. Uh, we have already seen this reaction many times. So I will start with the simple reaction. So in the ozone lysis, let's say we have the olefin and it react with the ozone. So what happens? This kind of intermediate ozonide gets formed. So the first step was if you the first step is just only the formation of the such intermediate in which the O3 will be the attached on the syn side of this group, and it converted into the ozonide by uh, oxygen insertion. So the oxygen inserted in between the carbon, which is double bonded, and the further conversion of this ozonide into the either aldehyde or ketone depends upon what kind of R groups are attached here. So let's say let's take here example. Here there is R is hydrogen. So this uh, ozonide then converted into the its corresponding acid. So let's say this is R1, and this will be the R1 C double bond OH. So this is the first step and first product, and second product in this one, because R1 and R2 both are, let's say here, alkyl group, so it convert into the keto form. So in the ozone lysis reaction, we get depending upon the what kind of R group attached, either we get acid or we get here a keto. And let's say if we add the instead of H2O2, we add the DMS at that time. If you perform the ozone lysis, so this R, let's say it's R1, this R1 converted into the its corresponding aldehyde, and this and other part will be in the keto. So if you want, uh, just a minute. Sorry, there was some interruption. So, all right, we'll start this analysis again. So, we already discussed regarding how we can get the acid as well as the ketone by using the if you use the H2O2 in the second step, we get the acid as a product as well as the ketone as a second product. In this case, let's say we have the primary alkene and the secondary alkene. Secondary alkene leads to the ketone, primary alkene leads to the acid. But let's say we have the we need to stop the reaction at aldehyde stage. At that time, we instead of using the hydrogen peroxide, we use the DMS. Let's say if you use the O3 and in the next step we use the DMS, at that time we will get the aldehyde as a product from the primary alkene, alkene which has the primary carbon, right? This one, so we get the this R1 converted into the R1 C double bond O H, that is aldehyde. So this is the uh, reaction also on the olefin, and this is the example that I have just shown. You can able to get the product from this one. So here, so this is the question. Uh, So we have given here the O3 and methanol, and the next step is the DMS at minus 78 degrees Celsius. So where the ozonolysis occur first. So if you look at the structure, this is the ester which has the OMe group attached, and here olefin. So in this case, what happens? The we'll get this minus 78. We have to remember. Right? So this case aldehyde and keto. This bond breaks into the aldehyde and keto. One end gives the aldehyde and another end leads to the formation of keto group in this one, right? Because there was methyl group. So this is the product for this one. So this is the also one of the oxidation reaction on of the olefin. So olefin bond get cleaves in this kind of ozonolysis reaction. So we see some more one of the previous reaction named as a Chugov elimination. So in this case, this is helpful for your solving assignment question. That's why I purposefully kept this. So and then we'll see sequentially the oxidation or the remaining oxidation reactions. But before going to the oxidation, in between I want to show the this is the thermal elimination of the xanthines uh, to olefin. So let's say we have the alcohol group and it reacts with the CS2 in terms of the NaOH. So it gives the formation of uh, and methyl iodide, it gives the formation of this intermediate xanthate, and this xanthate when we heat it, it gives the formation of olefin. So this entire xanthate as well as the proton which is seen to this xanthate group, it get eliminated to it get gives the uh, olefin as a product, and which is elimination. This elimination here syn elimination occurs, that we have to you have to keep in mind. So in most of the elimination which involve the pyrolytic elimination, the thermal elimination, that's pyrolytic elimination, almost 90% of this elimination, this type of elimination gives the uh, elimination occurs in the syn fashion, so that you have to keep in mind. And this is one of the this is the mechanism that already discussed, so you can refer this mechanism. Next to this Chichibabin pyridine synthesis, this is also this you can ignore as of now, because we'll discuss this in the later, and we directly move to the oxidation, that the oxidation reagent that are covered in the week 3. So this previous reaction, it will be helpful for your solving the assignment questions. So I will not go directly to the assignment question. So you can take the lead from the slides and select the correct answer. All right. So we are going to look at the methods that we can get alcohol to the that gives the oxidation of alcohol. The first reagent is the that covered is John's reagent, which is chromium trioxide in presence of H2SO4 and water, right? So the mechanism, general mechanism for all this one is almost similar that I have referred here. In most of the reaction, the mechanism is same. In this case, this B group you can refer as a not B group, the group Z. So this Z group, in case of the John's reagent, it will be this chromic acid CrO3H. So this chromic acid, this group, we can consider this one. So the base abstracts the proton and it gives the bond pair, electron pair between the carbon hydrogen bond shifted to the formation of carbon oxygen double bond, and the bond pair, electron pair between oxygen and the leaving group that goes away with the leaving group. In case of John's reagent, it is chromic acid. In case of Zorn oxidation, so as we already discussed in the previous, I think the last video, what are the reagent used in the Zorn oxidation? So auxiliary chloride and DMSO was the reagents, and the active the Z group in the Zorn oxidation is SMe2 plus. So this cationic species is Z group in this general mechanism. Further, we have also see the Dase-Martin for iodine-based oxidation as well as the IBX-based oxidation. So this is the general structure of the Dase-Martin reagent, and in this case, this entire group is as a will be act as a Z group, which is shown here in the general mechanism. Another example of the oxidizing reagent is TEMPO, right? TEMPO. This is a radical species. So this is the structure of this TEMPO, and it works in terms of the NaBr salt and NaOCl as a reagent. So this is the active species uh, which helps to give the oscillation of alcohol to corresponding ketone group. So, and along with this, there are some other oxidizing agents. So let's say example of the PCC, that is a pyridium chlorochromate, as well as we know there is also another reagent which is PDC. So which will discuss. This is the another reagent, and there is slight difference between the reactivity of this PCC as well as PDC. So we'll see general preparation of this PCC reagent. So sorry, the general reaction of this PCC. So let's say we have the alcohol. In this case, we have taken the example of primary alcohol. If you use the PCC, in this case, what happens? The two electron from the PCC, the alcohol get the two electron from this PCC, and it gives us the aldehyde as a major product. But instead of PCC, when you use the PDC, that is palladium dichlorochromate, instead of aldehyde, the reaction doesn't stop at the aldehyde stage. It gives rise to the acid as a product. So this is the example of PDC. And so there is the issue of selectivity. Let's say we add the PDC here. So we get along with this, although here added here in terms of the 1.5 equivalent, but still we get the, so when you perform the reaction in the DMF, we get the acid as a product. And when you perform the reaction, take this example. So when you use the PDC in 3.5 equivalent in the DMF solvent, it gives the alcohol. And in this case, when you use the PDC in 1.5 equivalent in the DCM solvent, so there is difference between the solvent. So when you use the DCM, the reactivity of this reagent in the DCM is slightly less. That's why we get the aldehyde as a major product. So we get 90% of the aldehyde. This alcohol stop, oxidation of this alcohol stop at the aldehyde stage when you use the PDC, but in DCM, and PDC in DMF gives acid as a major product. So this is the difference between the PCC and PDC. And also, let's say we have some here, the example that I have shown here in terms of the selectivity. So we have the starting material in this manner. So this is the starting material which has the 1,2 diol, and here, and the first step it react when you treated with the in case of the acetone. So it's like a protection, right? The 1,2 diol, we can able to protect this diol group. So we can selectively oxidize this group. So first step we have to protect this diol. So we get the protected diol, and when we reacted with the PCC, uh, in place of in the DCM solvent, we get the selectively this aldehyde as a product, and in later step we can able to uh, deprotect this group to get the remaining starting alcohol. So if you want to selectively oxidize this alcohol, so which is shown here in the green, so we can do that one by using this approach by protection followed by the oxidation, and further third step will be the deprotection of this uh, alcohols, alcoholic groups. So we can able to convert this in the next step into the so after deprotection we get this. So the selectivity is here it is important. So why we are using sometime the PCC and sometime PDC. So PCC stops the reaction at earlier stage selectively, but PDC not the case in the PDC. Uh, when we use the only one equivalent or slightly higher, not less than 1.5, and DCM solvent, we get some sort of selectivity. Alcohol, the oxidation of alcohol stop at the aldehyde state, but little excess can also leads to the formation of acid. And if you change the solvent, uh, let's say DMF, we'll get the selectively with the excess of PDC, selectively alcohol converted into the aldehyde. But when you use the equivalent amount of PDC reagent in the DCM solvent, we can able to achieve the selectively aldehyde. The next step that the next oxidation, the Zorn oxidation that we already discussed. So this is general mechanism I have pasted here, and here is the one of the example. So the utilization of this Zorn oxidation. So the DMSO acyl chloride in the DCM at minus 50 degrees Celsius, it gives the formation of this aldehyde as a product. DMP oxidation, that is Day-Martin per iodine. This oxidation also we have discussed earlier. So the summarized mechanism I have the mechanism that also we have seen, and these are some example that you can refer for solving this Day-Martin per iodine based oxidation. So here this was the one of the intermediate, and when we reacted the DMP in the DCM, it gives the 93% of the percentile of this one. So which group oxidize here? So this alcohol converted into the aldehyde in presence of this all uh, other functional groups are remain intact without any harm to the other reagent. But this is not the case when you use any other reagent like the Jones reagent and other. So this is also one of the important oxidation, the Zorn oxidation and the DMP oxidation. The further another reagent which is tetrapropyl ammonium perruthenate. So this is ruthenium based salt, and which used for the conversion of alcohol, primary alcohol to aldehyde. And so this is also one of the reagent you can able to use to if you want to convert the alcohol to aldehyde. You want to uh, aldehyde selectively aldehyde. So you can see this reagent and the general procedure also why it is important, because it tolerates the wide variety of functional groups, including the double bonds, enones, halides, as well as epoxide and esters, as well as in lactose. So that's why. So it does it not. If we have some examples here, let's say here we have here epoxides, also OTBS. So these are the functional group. So we can't use other harsh reagent in this case. So if you use this ruthenium based complex TPAP, so And in case of ENMO, we can able to selectively oxidize this primary alcohol without affecting the other functional groups. So that's why the selectivity of this reagent is important. And we can also, if you have some protein groups such as MEM, trityl, silyl, or benzyl ether, or THP, as well as the acetals, this group doesn't affected in this reaction condition. That's why the this uh, TPAP based oxidation reaction also one has some important in the synthesis of different natural products. Here there is example of alpha unsaturated ester and another alcohol. So this alcohol can easily convert it into the uh, aldehyde, and in first step it convert into the aldehyde. This is the first step. So this alpha unsaturated ketone is converted into the aldehyde. The first step was in this manner. Aldehyde, and this is the Wittig olefination reaction, right? So after Wittig olefination reaction, we get this second product. So this was the intermediate step one here. So this TPAP also has some applicability, and this also, as earlier mentioned, because it doesn't affect the function most of these protecting group, as well as it can work on the wide variety of it can tolerate wide variety of functional group, including epoxides or halides. So that's why it also have some synthetic utility. Another oxidizing agent is the activated manganese dioxide. This manganese dioxide is MnO2. So this MnO2 precipitate or powder also used for the chemoselective oxidation of allylic, benzylic, as well as propargylic alcohols, right? And oxidize faster than saturated alcohols. So let's say we have the saturated alcohol. I will just show here some example OH, and here there is, let's say, some any other alcohol group here R, H, and anything. Let's say R is equal to, you can take another uh, let's say we have here alcohol, and if you use the MnO2, sorry, something just happened. I'll just we have here CH2OH, right? So we have the two, this is one, and the two hydroxy group. And if you want to selectively oxidize uh, only one of these group, that is hydroxy group number one, we can use this MnO2 based oxidation, and it will give selectively the oxidation of only this functional group. This alcohol is converted into this aldehyde, not the this alcohol. So you can use this MnO2. I will just reconnect my writing board. Yeah. All right. Also, another example is this example of allylic, right? So if you have the benzylic alcohol, so if you want to select the oxidize this benzylic alcohol, this one, then we can use this MnO2 based oxidation. It will selectively oxidize this benzylic alcohol and keep withstand the hydroxy group, which is not a which is isolated, right? So it also has some synthetic utility if you want to use the if you want to selectively oxidize this one. But the disadvantage of this one is the it have we have to use about 40 equivalent of the MnO2. So the lot of MnO2 that we need to use. So if you are putting reaction from 1 gram of um, in, let's say, alcohol, which has the molecular weight 1000, right? So the one equivalent, for one equivalent we have to use the 40 equivalent, so which is almost a lot. So that much we have to use the MnO2 powder. So that's why this is not that much feasible, because a lot of much abundant of the MnO2 we need to use. But still, it is used for some, if you want to do selectively oxidation of this benzylic alcohol to the in presence of the other alcohol, then this protocol on small scale it is okay. You can use in the lab also. Further, another type of oxidation is the use of the barium magnet. So if you use the salt of barium chloride, the KMnO4 in NaOH and the Ki, it form a barium magnet, which is BaMnO4 twice. And this barium magnet, it is similar chemoselectivity as like the MnO2 in oxidation of alcohols, but readily available and do not require special treatment for its activation. As I have not mentioned earlier, that MnO2 needs to we have to do the activation of this MnO powder, which is mentioned in the slides. But this barium nitrate doesn't require prior activation. So here, difficult to activate difficulty associated with the obtaining highly activated MnO2. We need highly activated MnO2. Highly activated means, as you seen here, while preparing the MnO2 powder, so we are using the KMnO4 as well as the water. So we have to completely dry this, the moisture present in the MnO2, and that procedure is quite hectic. But in this case of this uh, barium nitrate, BaCl2, uh, such activation doesn't really required. So that's why uh, this barium magnet is preferential over the MnO2. And you can see the utility of this one. Alcohol can convert it into the aldehyde in presence of this barium magnet reagent in the at the room temperature. You can see the temperature also, because when you are performing reaction in the lab, then we need to consider all factors like solvent, the temperature. So at the room temperature, this alcohol can convert into the aldehyde. Another example here is shown for the oxidation of this alcohol, and in this case, the barium nitrate added in DCM, and it is added in quite excess. It leads to the formation of lactone. So what happens? The first oxidation of the uh, this is highly reactive, right? So it converts into the aldehyde, and this alcohol react with the aldehyde. It gives the lactone. So the oxidation of this CH2, the this hydroxy group, that is, which is allylic alcohol, occurs, followed by the lactone formation. And let's say if you use the only one equivalent of these, here we are using the 10 equivalent. If you use the one equivalent, then what happens? So because in the first step that the first step in this case, what happens? The first step was the oxidation, right? Oxidation of this alcohol to aldehyde. And the second step was the attack of this alcohol on the aldehyde. It leads to the formation of, again, alcohol. And the third step was formation of this lactone, because this alcohol form which further oxidize, right, into, that's why it formed the ketone. But if you have the limited amount of this barium magnet, then at that time what happens? It gives the first oxidation takes place, and then the only the lactone formation, sorry, the hydroxy group attack on the aldehyde, it gives the alcohol, right? So this step occurs only here, and we get the same acetal or lactal as a product, not lactone. Here lactal, Al, OL, right? Here ONE. ON stands for a keto group, and here OL, that is referred to the alcohol. So here we get the hemiacetal in this case. So these are the some utility of this barium magnet. And if we move to some other oxidizing agent, like that we have already professor has already taught in the lecture 15, that is silver carbonate on silite, that is a Penton's reagent. And this Penton's reagent, which is like Ag2CO3, which is on the silite, and in the benzene solvent, you can ignore, instead of benzene, we can use the toluene, and in reflux condition. So this gives the formation of this oxidize the silver carbonate, especially for small scale oxidation. And because the purification was easy, as they mentioned, followed by the oxidation, it follows the trend, which is allylic oxidation reactivity higher. So if you have allylic, then benzylic, followed by the secondary, then primary, right? Primary alcohol. So this is how the reactivity of this one. So if you use the only one equivalent, primary, then the selectivity here in this case, this is allylic, which has the uh, high reactivity toward this Ag2CO3 reagent, that is the silver carbonate or the Penton's reagent. So that's why only here oxidation of this reagent takes place. If you look at the second one, so in this case also the same, uh, this allylic get readily oxidized, and that's why we get about 80% selectivity. So let's say if you don't, in this case, the selectivity is important, because if you use any reagent, we doesn't have this selectivity. What happens? We can also get a product in this. So the product will be. So we can also able to get this product also in the reaction mixture. So what happens? The oxidation of this alcohol takes place, and also possibility this attacks on the aldehyde and get the product. So there are two possibility if we use the other reagent instead of, but in this case the selectivity matters. So because of this reagent, it's highly selective, and the allylic group is highly reactive than the normal saturated alcohol. That's why the oxidation of this allylic group takes place. So intermediate step will be in this one, will be this converted into the aldehyde, and followed by this aldehyde get attacked by the uh, alcohol group. So it convert into the lactal. So it will be OH, right? And this lactal is again then converted into the, because we are adding about 10 equivalent of this silver carbonate. So this lactal further converted into the here carbonyl group. So overall we get the carbonyl group as a ester as a product. So I will just mute this one. All right. So this is the Pentos reagent. And if you look at the one of the example of this one of the natural product, and why it is this reagent is important. So let's take, we have some group which is uh, this one, we want to do the oxidation of this group, and which also have other remaining group, although the oxidation of this one is not that much easy. So we use the this silver carbonate in terms of the benzene and reflux it. So in this case, we are able to oxidize this product selectively without affecting the stereochemistry of any other groups. So we get this about it is a reported reaction. It gives the 70% yield of this one, the final product, oxidized product. So this was the some of the reagents, oxidizing agents, and again there is another oxidizing agent that remaining that we will discuss today, and which is a tempo. So this is the tempo, basically a radical species. So this is the general structure of the tempo, and which involve the N oxide and radical N oxide radical. And this radical is like when you react this radical with the alcohol in presence of the NaBr as well as the NaOCl in the in the DCM. It at 0 degree Celsius, it gives the formation of alcohol to aldehyde. So this reagent also used for the oxidation of alcohol into the corresponding aldehyde, and the chemoselectivity it react for primary alcohols. So the primary alcohols is like highly reactive towards the tempo, and secondary alcohol, although it the reactivity it shows some reactivity to the secondary alcohol also, but the thing is it shows the uh, slow reaction with the secondary alcohol. That's why if you want to selectively oxidize, let's take the another example here. So this is the secondary alcohol and this is the primary alcohol, and if you use this tempo, uh, so we can able to selectively oxidize the primary alcohol here. So you will get the aldehyde from this primary alcohol. Secondary alcohol doesn't get affected in this one. So this secondary alcohol doesn't get react. So the primary has the higher reactivity than the secondary. So that's why different reagent is required for carry out the different type of reactions depending upon what we are looking for. So in this one, we want to convert only the primary alcohol, this alcohol, and that's why we can select the this tempo as a reagent, and so we get the aldehyde as a product that desired that was the desired product. So this was the reagent, and there is another oxidizing agent is the cerium ammonium nitrate that we generally in the lab we refer as a CAN. So this cerium ammonium nitrate reagent, which is a salt of Ce and the NH4 twice Ce, NO36. So this is the the full form, full structure of the cerium ammonium nitrate, and it works in presence of the acetonitrile at 80 degrees Celsius. So obviously, you need high temperature, but it selectively oxidizes the secondary alcohol over the primary. So if you look at the previous our reaction, reaction of the tempo. So here chemosylated oxidation of the secondary alcohol group in presence of the primary alcohol. So this is the utility of the this cerium ammonium nitrate. So in this case, only this compound, this alcohol get converted into the corresponding keto form, and this primary alcohol, this was the primary, this is all the secondary. So the primary alcohol remain unaffected. And if you look at the yield of this reaction, it is about 90%. So it chemoselectively oxidize the secondary alcohol. So let's take the example. If you want, so this is the one of the alcohol, and and let's say we want to oxidize this, or another way, let's say, so this is the A and the B. So you can select any one of these reagent. So let's say this is the question. If you want this product, so in which the the secondary alcohol converted into the keto, but primary remain unaffected. So in this case, we will use the ceric ammonium nitrate, and the case in which we want oxidation of the primary alcohol, not the secondary alcohol. In this case, we use the tempo reagents. So these are the some synthetic utility of this oxidizing agent. There are still some reagent that are remaining. Let's which is used for the oxidation of acetylons. The previously whatever oxidizing agent that we have seen, which was the oxidation for the primary, secondary, or the oxidation of primary or secondary alcohols, as well as the oxidation on the olefins, that Woodward and the previous oxidation that from the diol formation on the olefins. It gives the Woodward give the syn diol, previous give the trans diol, right, or the anti diol. Later, we also see the example of the ozone lysis, because that also the kind of oxidation on the olefins. Further, we have seen some oxidizing agent like including PCC as well as the PDC. Right. The PCC selectively gives the aldehyde. PDC we can able to get the acid as well as the aldehyde depending upon what solvent we are using. Further, Soren oxidation that we have already studied many times. Then the DMP oxidation. This also we have seen. Further, the tetra propyl ammonium perruthenate, that is a ruthenium based reagent which is used for the uh, oxidation, and it is tolerate to many variety of functional group including the double bonds as well as the enone and the halides. And for also in presence of the protecting group, if we have our molecule have some protecting group like the MEM, tritylsilil, benzyl ether or THP, acetal, they are not affected in the reaction condition of this TPAP oxidation, right? Further, we see the use of the manganese dioxide based oxidation. So this manganese dioxide oxidize the allylic benzylic as well as propargylic alcohol over the oxidation of this primary. So the primary alcohol doesn't get not primary uh, saturated alcohol, which is isolated from the like the alcohols like this one. So which is doesn't which is not a allylic as well as not a benzylic or not a propargylic. So this kind of uh, alcohol group not get oxidized, but it readily oxidize the allylic as well as benzylic, propargylic, that kind of functional group. So here example of the benzylic, and but we have see also the drawback of this MnO2 based oxidation. So the drawback was we need to use about 40 equivalent of this MnO2, and also the activation of this MnO2 is not that much easy. That's why the another reagent that we have seen, so which is the barium magnet, and this barium magnet which is uh, barium dichloride with the KMnO4 uh, and NaOH and Ki, it forms the BaMnO4 twice reagent, and this reagent also do the similar work as like the MnO2, and also in this case we can able to get the aldehyde from the alcohols, right? The only thing here in this case is like we don't require to use that much amount of the barium magnet as like MnO2. So this is the one of the advantage of this barium magnet reagent. Further, we see the other reagent like the Pentone's reagent, which we have already seen. This Pentone reagent it oxidize the allylic, and in the priority order, allylic, benzylic, then the secondary, and then primary, right? And later we see the tempo. The tempo also reactivity of tempo is primary is highly reactive than the secondary, so it selectively oxidize the primary alcohol. Further, we see the sodium nitrate which selectively oxidize the secondary. So these are the some oxidizing agents. So hope you have uh, got favor of what are the different oxidizing agents that we generally use in the day-to-day life. And these are the other oxidizing agent which is for the specially used for the acylons. Acylons is referred as a diesters, right? So you have already heard about the acylon condensation reaction. So this oxidizing agent that we'll see in the next lectures. But before going to uh, discuss this acylon, we'll see some more the problems. So which will be helpful for your solving assignment question. This is the one of the question that I have directly taken from a reference book. Let's solve the this reaction by what are the by utilizing the reagent combination that we have given in the question. So we have given the MgCl, RMgCl, which is a Grignard reagent. So this Grignard reagent directly attack on the carbonyl. That is obviously the because it is hard, and if you do workup, it convert into the alcohol. And in this case, when you use the PCC, in when you use the PCC, what happens? The trans we have already seen one of the example. Generally, we draw in this fashion. So so we know the we have seen this one of the example, right? So let's take here, let's say we have this case and we use the PCC. What happens in the tertiary alcohol with the double bond? When you use the PCC, so double bond move to here and the carbon carbon goes to here. In the similar manner, this was the tertiary alcohol and we have here the double bond here. So this is a kind of alpha beta unsaturated carbon here. So it is transposition of the carbonyl. So this is carbonyl transposition. So this instead of since here there is a it is tertiary, it show the 1,3 transposition of the carbonyl. So we get the aldehyde here, OH. So we get it is in the 87 percentile. This same reaction occurs with the IBX that also we have seen earlier. And this 1,3 transposition occurs with this. Another exam question is when you react with the methyl lithium, again here also the same, because it is a hard nucleophile, you directly attack on the carbonyl carbon, and when you use the PCC, it is also the 1,3 transposition. So this is the product which is we get here in 94%. So this concept is used for your solving one of the question from the assignment. The next question is, all right, so the RMGX, that is Grignard reagent, you directly attack on the carbonyl, obviously. So it gives this carbon-carbon in 63% and followed by the PDC. So this same concept, 1,3 transposition, that no need to discuss again. So again, the next question is the reaction of this starting material with the butyl lithium. The butyl lithium obviously abstract the proton followed by the DAPCO in the THF and the ketone. So what happens? This entire group is the pH group, right? So butyl lithium extract the proton from the CH2, let's say CH2H. So this is CH3, I just split it. Butyl lithium extract this proton, right? It forms the PHS CH2 negative. And when this PHCH negative react with the this kind of group, so it is directly react to the carbon carbon, because the CH2 negative directly react to the carbon carbon and it gives the formation of the product upon hydrolysis, right? So it gives the 95% of this product. And again here the same concept of the 1,3 transposition, the PCC, right? The PCC, this ultrasound is just to in the paper they have reported by using the ultrasound the reaction is much faster, but it is not really necessary. Always we need to use the ultrasound. So when you use the PCC, so what happens? The same 1,3 transposition, because this is a tertiary alcohol and it gives the ketone group formation at this position, right? So this concept you should aware about this one. The professor has already discussed the detailed mechanism of this 1,3 transposition, how this carbonyl transposition occurs. Then again, we have one of the reaction, which is a Fleming-Kumada oxidation reaction, which is the that in the 15th lecture or 16th lecture or in the next week that we are going to learn. So I will just show one example because this the question someone asked in the question and answer forum. So I think this was the question. Yeah, the question was in this reaction. Uh, so first we will discuss this. What is this Fleming-Kumada oxidation reaction? This is the stereoselective oxidation of alkyl silanes into the corresponding alkyl alcohols using per acids. So we have the alkyl silane here. Let's say we have the alkyl silane. It reacted with the HX. In this case, let's say HF. And this is the per acid followed by the hydrolysis, which gives the alcohol with the retention in configuration. So this is the example. Let's say this the let me check. Yeah, this is the starting material, right? So what happens? Uh, this epsilon addition of this acid, because we are using per acid. So it forms the H plus plus here and the cation in the aromatic ring. And we are using, because we are using the strong base, so strong acid, right? This X minus, in this case, let's take the F minus attacks on the Si, and it forms the intermediate like this. And when it reacts with the per acid that we are added already, the per acid attack on the silicon, and X get removed. So and it abstract the proton from the obviously it can abstract the proton. So aromatization again takes place. So it will be a HX negative, right? And it forms the intermediate in this fashion. And also, if we this is the per acid, right? So this bond pair between this one get used for the sorry, uh, yeah, this is the migration or the rearrangement, right? So this rearrangement of this RCH, sorry, RC, R dash, this takes place to the acid, sorry, the oxygen, and this ARO, C double bond O minus get removed from this one, and it is kind of this entire group is getting migrated to the towards the oxygen. So the oxygen get inserted between the carbon and the silicon, and followed by the again the next per acid attacks on the Si. It gives the intermediate in this fashion. So which has the OSI, O peroxide linkage bond, and which is then again removal of the uh, Si, again removal of this acid, the per acid. So here utilize the first equivalent of the per acid, right? If you count first equivalent, this is again second equivalent, and this is again third equivalent of the per acid. It leads to the formation of the intermediate, and followed by the whatever the eliminated per acid, the negative, it will be a AR C double bond O negative, which attacks on the silicon, which leads to the intermediate, followed by the hydrolysis of the hydrolysis. It gives the alcohol. So there are almost one, two, three equivalent of per acid is getting utilized, and whatever the acetate or the here in this case benzoate anion, which attacks to get the intermediate. Let's say this is the intermediate A, and which on hydrolysis it gets the alcohol. So there are obviously too many steps involved, but if you look at directly the reagent, in you can directly, if you look at the reagent combination, just keep remember the reagent combination. This is the HF per acids and its hydrolysis. It gives the uh, alkyl silane to the corresponding alcohol, and the geometry will remain same. So this was the Fleming-Kumada oxidation, and yeah, the same mechanism that given here, so that you can remember to solve the question, right? All right. So if you have any question, then we'll discuss that question. Uh, yeah, these are the some question. So first question was based on the IBX, right? That we have already seen, and it also already mentioned by the professor. So why the secondary alcohols, IBX, in the IBX mediated oxidation of secondary alcohols, an increase in steric hindrance on the substrate alcohol cause whether increase the rate or whether decrease the rate, that you have to just select. The second question is the very similar manner that we have already discussed. That is the IBX with the methyl iodide, it gives the alpha beta unsaturated ketone, right? And then further it react with the methyl lithium. So when it reacts with the methyl lithium is hard nucleophile, so it directly attack on the carbonyl, So I'll try to roughly draw this one. So the first step was the ignore the number of this double bond O, this alpha beta. The second, after first step, when we add the first, when you add the second, then what happens? The methyl lithium directly attacks here. So this OH, then here there is methyl. So this is the after second step, and after third step is the PCC, the PCC oxidation that we have already seen, the transposition of occurs, right? So the ketonic group will be migrated. So after third step and after fourth step, this is the copper salt, right? So the copper salt, which is obviously a soft nucleophile because it's copper. So it addition takes place on the fourth position. So the product will be, which has the methyl group also on the same carbon as well as this. This group is also on the same carbon, and here there was a keto group, right? So this is the product which is getting formed in this reaction. So you can see here. All right, so this is the product is getting formed in this reaction, right? So you can able to solve this question. They are not like very much difficult. The next question is the major product formed in the following reaction with one equivalent of the reagent. So we have given this one equivalent of the reagent, and here also you have to uh, see the product or products. So it will be a multiple choice also. It can be. So two equivalent of Ag, silver benzoate, right, and iodine. So this is the pre-washed, right? Pre-washed oxidation, and it will give the anti-diol, right? So that you have to keep in mind. The fourth question is the major product formed in the following reaction. The ACO2 based oxidation that we have already seen. Then the followed by the LiOH. LiOH generally used for the hydrolysis. The silver, this reagent Ag2CO3 and silyte and benzene. This oxidation reaction also we have already covered, followed by the hydrolysis, right? So I don't think there is difficulty in solving this question. The fifth question is based on the ruthenium RuO4 oxidation. The sixth question is based on the same RuCl3 NaIO4 oxidation, followed by the in presence of the acetonitrile and carbon tetrachloride. So this is the sixth question. Seventh one is the also the similar based on the ruthenium trichloride. These all question you can able to solve if you just look at the video of the 14th lecture and 15th lecture. That's much more than enough. And the next question is based on the Fenton's reagent, and in this case it mentions the Fenton's oxidation of hydroxyl groups labeled in A is much faster than the hydroxyl group labeled in the B. So, and this is because the most favored conformation is, so most favored conformation you can able to easily select from this one. So first which conformation is the correct, that you can able to, you have to look at. So let's take the example of these two groups. So these two groups are the anti to each other. If you look at this one, these two groups are anti, okay, anti, it's okay. In this one, these two groups are the same to each other. This is obviously the wrong option because the conformation is also is wrong. If you look at the next one, so the OH and the TBU, this is the right, this is seen, right, and the fourth option is the TBU and OH is the same. Okay, so we have neglected this option. Again, if you look at this methyl and the hydrogen, they are also seen to each other because both are shown by the beta bond. So in this case, the methyl directing upward, hydrogen directing downward. So obviously this confirmation is wrong confirmation. And then you can able to get remaining. So hydrogen and the methyl, this is on the scene. Hydrogen and methyl is on same side, right? So you can, there will be option between these this one and these two. So we only two options are remaining because this confirmation are the written in the wrong. So these two confirmation are wrong confirmations. Next one is if you look at this hydroxy and methyl is seen to each other. Hydroxy methyl is seen. Hydroxy methyl is seen. Okay. Is anything else that we are missing in from this row? All right. Uh, there is huge mistake in this one. So if you look at the bond, how many bonds this carbon have? It's one, two, three, four, five. Carbon with five bond, right? So obviously this option is wrong. So you can able to get. So these are the some trick you can apply for the CSIR, NET or GATE examination. I think you guys have the GATE examination in the next week as well as the CSIR uh, NET examination in the after I think at the end of this month. So you can apply this trick to solve the questions. So just neglect the whichever option is incorrect, neglect that first, and then move uh, to solve the question. So hope you guys have able to solve all the question and enjoy this lecture today. So does anyone have any question? All right, if you don't have any question, then I'll stop recording this one, and I will record upload this one on the YouTube. You will get it by mail